Artikosa here. My advice to all of you as I'm recording these videos for you, please make sure you understand and please keep on supporting as I'm imparting you or sharing my knowledge with you. Also share this knowledge with others, and it doesn't stop you for looking for more information or seeking for more information. And another thing is that cramming is not a solution, because if you cram, you'll never know. What your mind knows is to forget. So if you don't keep on reminding it, you forget forever, which is a disadvantage, especially if you are doing a course that will require what you did before. So you always have to go back, waste time for nothing. So, but if you understand, you'll never go wrong. As long the mission is for you to understand and study, then you'll pass. Don't be concerned more about passing, but understanding is the main key to all, to success. So please, you are here to train your brain or to teach yourself something out of this degree that you're doing. So take it important and serious. That's my advice. You all welcome. Keep on subscribing and supporting me as I will support you, sharing with you the marvelous information that I have. We can recap on what we'll be doing. So let's just focus on mathematical logics laws, actually the proofs, and that's all. Hello everyone, I hope you are fine. You're having a very much wonderful day. So I've realized that most of the students are getting lost when it comes to logic laws. So I've decided today I'm going to focus on mathematical logic proofs. So right now, let's start by proving using logic laws. So we have 8 important laws under logics which applies the same inside. So in this case, given three statement P, Q, and R, and we're going to denote F to be the false statement and T to be the true statement. So the identity law, as you can see it, is that the union of P and a false statement will get P, and the intersection of Q and the true statement will get Q. So this sign, as you know, as the logical equivalence. So for the domination law, is P union T, we get a true statement. R intersect a false statement, we get a false statement, because the intersection of a false and a false is a false. It will only be true if both are true, as you recall. So ID important law. So this law is when we take the union of a statement and the intersection of a statement with itself will obtain that particular statement. So we also have commutative law. So commutative law, we can just swipe the statement P union Q is Q union P, and also Q intersect R is R intersect Q. So as I said, equivalence is saying. So associative law. So under associative law, it's a matter of associating the brackets. As you can see here, these brackets over here, they remove them this side for associating the brackets. So it works here where you can see it's P union open bracket, Q union R close bracket is equivalent to the P union Q union R. So same thing for the intersection. We are just associating the brackets or moving the brackets, as you can see. So for distributive law, I've explained this. You can take it as addition and multiplication. If I recall, I showed an example like this. If maybe I'm giving x plus y multiply by z. I can distribute this into x, z plus yz. And that's what is actually occurring in this. So you can see that it's P union open brackets into Q intersect R. We can write it as P union Q intersect P union R. So even here on P union Q intersect R can be written as P intersect R union Q intersect R by distributive law. So complementation law. So this is the negation law. So we are contradicting the statement. So not P is the contradiction of statement P. So if we're going to contradict again the contradiction of statement P, we get P. So this one, P implies Q, is equivalent to this, not P union Q. So negating it will get P intersect not Q. And this is due to De Morgan's law. And De Morgan's law states that the negation of P union Q is equivalent to not P intersect not Q, and the negation of Q intersect R is equivalent to not Q union not R. So let's just do some applications. So I'll just only do 3 examples and I will apply the laws, but basically I will be focusing on the De Morgan's law, associative law, and distributive law. So yeah, you'll understand as we go. So let's just do this 3 examples. So we talk about the logical equivalent statement. So we are trying to show this one. Given this example, we have to prove that this P implies Q union R is equivalent to P intersect not Q, which it implies R. So to do this, as we said, we're doing the application, we are applying the laws of logic. So in this case, the first thing we know, P implied Q from here is the same as not P union Q, so we'll apply the law. So here we'll say this part of P implies Q union R is equivalent to not P or Q union R. So this will be by implicit definition. Then we continue, we'll say this part is equivalent or continuing to this union Q union R by associative law. We continue, this part is equivalent to then the negation of P intersect not Q union R by De Morgan's law. We continue, this part is equivalent to P intersect not Q implies R by implicit definition again. and we are done proving that these two are indeed equivalent. So we use the laws to prove that. So can you see how easy it is? It's all about the matter of understanding. So let's continue and do the second one. Okay, consider this second example. A intersect B implies C is equivalent to A implies C union B implies C. So we have to prove this. Let's start. Remember, we're going to use the laws, right? So we start with this part. A intersect B implies C. So this, as you know, is equivalent to not A intersect B union C. As you can see, by implicit definition. So we continue. What is this equivalent to? It's equivalent to not A intersect not B. Oh, I have to change the intersection now. Union not B inside brackets union C by De Morgan's. So this is equivalent to not A union C union not B union C by distributive. So this part is equivalent to A implies C union B implies C, and we have proven that these two statements are logically equivalent. So it's also by implicit definition. So you see how easy is this. So let's do the last one on this logic laws. Okay guys, this last interesting example here, yeah, you'll find it interesting. So we are given that P intersect Q, not P intersect not Q is equivalent to P by conditional Q. So in order to show this, we have to show that this part is equivalent to this part. And remember, now we are using the logic laws, so we need to apply those logic laws. So to do that, we are going to show that this part is the same as this part. So let's start. So we'll write this part as it is. P intersect Q union not P intersect not Q. So to show this, it's up to you. You are going to use the distributive law first. So it's either you use this part, you take it as your x, or you take this other part as your x. So myself, I'm going to choose this other part as my x. So using distributive law, this part is equivalent to. So I'm going to treat this thing as one thing, then I apply distributive law. As you can see, it applies. So which means the first one, I will have P or X, where X is this one. So complement of P intersect not Q. So this, as I told you, then this sign, as you can see it, intersection, then I have Q or x again, where x is still the same as not P intersect not Q. So you can do it in your own, where you first use x, then you come back and substitute, we get back to this solution. So this is by distributive law. Understand? So continuing furthermore, what is this equivalent to? So we're going to apply distributive law on this part again, and also this part, and our reason also will also be by distributive law. So this is equivalent to, for this part we have P or not P intersect P or not Q. So by distributive law, this part and this part are the same. So we intersect with this other part, we apply the distributive law, so it's Q or not P. Then we're going to intersect this with Q or not Q. So this one is by distributive law again. So we are going to simplify now this part P or not P, and also Q or not Q by domination law. So let me explain clearly what does this law mean. So this one is, you can also write it this way: P or not P is equivalent to a true value. That's domination law. So even here you can write R intersect not R is equivalent to a false value. So that's how domination law works. So we have this here. So by domination law, this part is a true value, so it's equivalent to T. Then intersect, we have this part P or not Q. As I am explaining here, remember, don't forget this side also, we have Q or not P. So it will intersect again a true value. So this is by domination law. So true value is dominant. So in this statement. So we continue. This is equivalent to, remember, a true value intersect a statement is that statement. And this is by identity law. So here we'll apply identity law. So this one will going to have P or not Q intersect Q or not P. And this one is by identity law. So we'll go further. So what is this part? This part, how can we write this part? This part can be written as not Q or P intersect not P or Q. By which law? By commutative law. Commutative law. Continuing, where this is equivalent to, what is this? Q implies P. Intersect P implies Q by implicit definition. So where this is equivalent to P by conditional Q. So we have proven that the two statements are logically equivalent using the laws. This is very much interesting. Just look at it and try to digest it. Okay, let's just do the second part. Here we are proof using flow of argument. So I won't waste more time since I explained to you what is argument. So you are given these statements. P union Q. You are given Q implies R. P implies R. You have to conclude on the true value of R. So since these are the true three given statements, it's not different from writing it this way as the intersection. So you can allow me to erase this. So let's solve. So for these ones, as you can see, to be true, we have to use P union Q in this case. And for the union, it's either one of them or both. So we have to prove in all those conditions if this thing is indeed the case, it is true. So now we start with suppose both are true. So we know that Q implies R and P implies R also are true given statement. So R is true. We're done with our first case where both are true. So suppose the second case, suppose P is true and P implies R is also true. Then R is true. The last case, suppose Q is true and also Q implies R is true. Then R is true. So we can conclude that therefore R is true regardless of the three cases. Therefore R is true and the statement is valid. Regardless of the three cases, R is true and the statement is valid. Hopefully, you did try to digest and understand what's going on. So, you'll be fine. Okay, guys, we're proceeding. This is our last part. So part 3, we're proving using the methods of proofs. So I just want to clarify here. I'll just do one example for each. So mathematical, logical proofs as well part of that. So in this case, you have to understand what are integers. So two integers a and b can be classified as even or odd. So you can see any integers. So an even integer a can be written as 2x, where x is an element of integers. So in this case, we can say our a is divisible by 2, or we can say our a is divisible by x, because if we say a divided by 2, we'll get x, and also if we say a divided by x, we'll get 2, which is the integer, and also x element of integer. So in this case, the odd integer, it will be defined by 2y plus 1, where the odd integer, it will be b. So y, an element of integers. So we say two integers a and b are consecutive if they follow each other. So example, b can be written as a plus 1, or a can be written as, which implies this, a can be written as b minus 1, as you can see. So an integer b is divisible by integer a if and only if b is given by ak, for k also an integer. So in this case, for an example, we can say b is 2a. This one is an even integer because of these 2, since a is an integer, and also it is divisible by 2, and also it is divisible by a, as you can see the way I defined it. So this one we're going to prove it by cases. We can prove it anyway, but I'll choose to prove this by cases, that if a equals to b, then a plus b equals to 2a. So now I want you to understand the direct proof. So we start with the direct proof. So under the direct proof, we are proving directly that P implies Q. So by assuming P will get Q, because remember, we're having if P then Q. So we can just do one example, as I said. So we can consider this one. If A and B are consecutive integers, then A plus B is odd. So we can just do this directly, as I told you, i.e. It's either we can write our B as A plus 1, or we can write our A as B minus 1. So we can prove for these two directly. So let's see for this one if it applies. What about A plus B? A plus B can be written as A into A plus 1. So we can see we get 2A plus 1. So since we know that this A is also an element of integers, therefore this part will be odd. And we can also do it by the other way around for this one, for A plus B. Using this one now, we can write it as, now we can say this is the same as B minus 1 plus B. So this I can write it as 2B minus 1. So I can factor out the negative here. I can have something like this. You'll understand how it works. this thing, 2b negative 2b plus 1. We can see regardless of this thing will be odd because we're still adding 1 here. So therefore, it's also odd. So you see how it is going. So you'll understand more about this. So let's just now go to this part here, indirect proof. So I'll start by counter example. The first one will start by counter example. So in here, we're just proving by giving an example that our statement it is true or false. So I'll just give only one statement. So we can take this one. For every x, an element of real numbers, x squared is greater than x. So is this statement true or false? So let's see. Is 0 squared greater than 0? No. Is 1 squared greater than 1? No. So what about, is negative 1 squared greater than 1? No. So it does not apply. So this statement is false. So our counter example will be for absolute value of x less than 1. In other words, your x will be between negative 1 and 1. Your x can take any values between negative 1 and 1 in this statement. It won't be true, it will be false. So this is proved by counter example because we are proving that the truth value of the statement by giving an example. So this one is very much clear. So you get it. So the second one, the proof by contrapositive opposition, as I wrote before. So in this one, we are trying to prove that P implies Q by proving that not Q implies not P. In other words, we just assume the opposite. So let's just do this one that we are having here. We can do this one. If A equals to B, then A plus B equals to 2A. So we can do this one with this one. So well, if A equals to B, then A plus B equals to 2A. So our statement P will be A equals to B, and our statement Q will be this, will be A plus B equals to 2A. So we just say, suppose A plus B is not equals to 2A. So if A plus B is not equals to 2A, then we just have to solve for what A is equal to. Is A equal to B? Let's just check. So this implies that A plus B minus 2A is not equals to 0. So continuing, we're having something like this. We're having B minus A is not equals to 0, which implies that A is not equals to B. And A is not equals to B is the negation of P. So, by contraposition, if A equals to B, A plus B equals to 2A. And that's how we prove by contraposition. So we are proving that P implies Q by proving not Q implies not P. So hopefully you are getting along with this. I hope so. So just pay attention. We're still under indirect, so let's do proof by contradiction. So proof by contradiction. So in here, we are going to prove that P implies Q by proving the negation of P implies Q, which you know is equivalent to P intersect not Q. So it's not different from contraposition, so but it's contradiction, so we just difference it on the conclusion. We can prove the same thing, but not to confuse. I saw it very much important to just explain this one. So I'll do the one which I gave you as a activity to do, then you verify for yourself. So we are about to show that the square root of 2 is irrational. So you know what are irrational numbers, are numbers that cannot be expressed in terms of fraction. They are just those decimal numbers which can only be expressed in form of a square root, yeah, you know them. So for us to prove by contradiction, this is actually statement P implies Q on itself, so we just have to assume the opposite. So as I told you, we prove by contradiction we are negating, so this is not different from complementing the statement. So here our proof will start by suppose square root of 2 is rational. I.e., the square root of 2 can be given by x and y, where these x and y are the smallest integers, and they have no common divisor. So that's how we define these to be square root of 2 to be rational. So in this case, we're going to deduce what is x and what is y. So we have the square root of 2 is equals to x divided by y. So we can square both sides, which means this implies that 2 is the same as x squared divided by y squared. So making x squared the subject of the formula, we have x squared is equals to 2y squared. So since we said x and y are integers with no common divisor, it means x and y are irreducible. That's how a set of rational numbers is defined. When we divide x and y, we must find it irreducible. For example, 1 over 3, 2 over 3, 2 over 5, all of those numbers. So that's what we're talking about, rational numbers. So in this case, we found out that our x squared is 2 times y squared. So what does this imply? It implies that our x squared is even. And if our x squared is even, so x is even. So which means we can write x as 2k for k an element of integers. So if we can substitute in here, we are going to get what? We are going to get 2k squared, or 2k all squared is the same as 2y all squared. So we can make y squared the subject of the formula. Y squared can be written as 4k squared divided by 2, which is 2k squared. And this I can equate it to 2p. So we can see this y squared is also even. So if y squared is even, so which means so y is even. So you know that. Continuing, this is contradicting our assumption because x can divide y since it's even. Remember, when you say it's even, it can be written as 2r, the other one we can write it as 2q. So 2r over 2q divide each other. So and we assumed that it's rational and they cannot divide each other. So here, so x can divide y, which is a contradiction. So it's contradicting our assumption. So we can conclude that by contradiction, square root of 2 must be irrational or is irrational. So that's how we do it. There are a lot of examples to show on this, but you just have to understand, nothing more. Let me just give you a chance to try to digest this, so yeah. And you'll get it very much quite well and interesting. Okay, as we proceed, we're going to prove by cases. As I promised, we're going to prove this one. If a equals to b, then a plus b is 2a. So here we're about to prove this one. If a equals to b, then a plus b is always even. So in this case, we are going to have case 1, which is a is even. Case 2 for a is odd. So case 1 for saying a is even can be given by b equals to 2x. So which is the same as a, for x an element of integer. So if we deduce a plus b, we are going to get 2x plus 2, which is 4x. We can take 2 out as a common factor, then we're left with this 2x, then we have 2z. For this z is the same as 2x, also an element of integers. Therefore, that prove for case 1, if a is even, a plus b is even, since a equals to b. So for case 2, what about if a is odd? So a can be given by 2y plus 1, which is the same as b. So for y, an element of integers. So I'm looking for a plus b. So I have 2y plus 1 and 2y plus 1. So in this case, I'm going to get 4y plus 2. So I take 2 out, I'm having 2y plus 1. So this 2y plus 1 can be written as w. For w equals to 2y plus 1. So this being an element of integer. So this proves that a plus b is even. So we have proven that regardless of case 1 or case 2, if a equals to b, then a plus b is always even. So that's how we prove by cases. Thank you for watching. Keep on subscribing. I'm Artikosa, by the way.